Prabhupada ki jai. Hare Krishna. Welcome everybody to today's session on Learn Gita, Live Gita. So we were discussing yesterday about a very interesting topic called Absolute Truth. So we discussed yesterday that, first of all, the importance of the quality of neutrality to be able to understand the concept of absolute truth. What's the reason? The reason is that the concept of absolute truth is indescribable, it's inconceivable. So whatever understanding we have, it is limited. Therefore, the best understanding is to explicitly state that our understanding about absolute truth will always be limited, right? That is what Chaitanya Mahaprabhu has taught. Achintya Bhedabhed. Achintya means it is beyond our imagination, beyond our conception, beyond our reach. Achintya means it's really so huge that we cannot grab it completely. So, but we can. So, but then why should we study it? Because we should study it because the more we study, the more we understand, the more we become satisfied, the more we feel blissful. So Krishna is infinite, but even if we get a slight glimpse of him, which is a proper glimpse, then it satisfies us to the full extent. Hare Krishna. So let's start today's discussion with prayers. Namo Vishnu Padaya Krishna Preshthaya Bhutale Srimate Bhaktivedanta Swami Niti Namane Namaste Saraswati Deve Gauravani Pracharine Nirvishesh Shunyavadi Paschati Veshakarine Jaya Shri Krishna Chaitanya Prabhu Nityananda Shri Advaita Gadadhara Shri Vas Adi Gaura Bhakta Vrinda. Hare Krishna 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 Hare 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 Rama 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 Hare Hare. So let's start with this section on infinity. So there are varieties of concepts of infinity. For example, if you go and walk along the bank of the ocean, you will see the sand particles. They appear to be infinite. Then you feel the vastness of ocean. You have another experience of the infinity. You ponder over the limitless sky, then you have another idea of that infinity. Someone, say a physicist, who has dedicated his whole life on contemplating on the gigantic nature of this universe, will have another understanding of this infinity. A mathematician will encounter this concept of infinity from another angle. What is an infinity? Okay. There are so many examples given here which appear to be like infinite, right? We have ocean. Ocean looks to be infinite. Sky appears to be infinite. Sand particles on the beach look like infinite. Then this is the notion of infinity. So what is actually infinity? So if we consider 10 to the power 99999 or factorial 99999, they are very big natural numbers, but still they are not infinity. Okay, maybe just a wake up question. Which one is bigger, 10 to the power 99999 or 99999 factorial? Let's say who answers first. Which is bigger, 10 to the power 99999 or factorial 99999? Which one is bigger? Okay, Rajkumar Prabhu says 10 to the power 99999. Kunal Prabhu says the second one. So we have a tie. Who is the tiebreaker here? Who can break the tie? can break this tie? Nobody's answering. That's strange. I thought this is just a wake-up question. Everybody will just wake up. Who all are there? Rajat Prabhu, you want to answer? Abhishek Bansal Prabhu? Or Archit Prabhu? Abhishek Bansal Prabhu says 10 to the power. Rajkumar Prabhu says 10 to the power. Kunal Prabhu says 999. Archit Prabhu, what is the answer? Second one with a question mark. Okay. Who is left? Abhishek Bansal Prabhu has given, Archit Prabhu has given, Kunal has given, Rajat. Only Rajat Prabhu is left. Second one. Okay. So majority goes to second one. Okay. I didn't think that this will be that difficult a question. Okay. Okay. So what is 10 to the power 99999? It means 10 into 10, and this goes on up till 9999 times, right? So there are 99999 terms, of which 10 are multiplying. And the other number is, how many terms are there? So 99999 terms are there, but the first term is 9999, second term is 99998, next term is, and each term is bigger than 10. Each term is much bigger than 10. Of course, the last 9 digits will be less than 10, but mostly they are, other terms are all bigger than 10. Right? Is this a good reasoning? In the second, so both these, if you expand them, both will have 99999 terms getting multiplied. In the second one, every term is bigger than 10. Means most of the terms, like almost all the terms are bigger than 10. So naturally the second term is bigger, right? No? Okay. Think about it. So sometimes one may assume that the number of sand particles in the entire Earth's planet may tend to be infinite. But a scientist very well knows that the total number of sand particles is a finite quantity, just as the number of molecules that this Earth consists of. Right? So even if somebody may say that number of sand particles on the surface of on a beach appear to be infinite, but they are finite, right? You know how to find the number of sand particles. You find the total volume of the beach, approximate it with some upper limit, and then find the volume of one sand particle, and then you can find an upper bound on the number of sand particles, right? So you can find an upper bound on the number of sand particles. So it is not infinite, it is a finite number. It is upper bounded by a finite number. So it is finite. Okay, so that's the advantage of knowing some mathematics, that you can know what is not infinity. Okay, let's ask this question. Is the number of photons emitted by all luminaries within the universe infinite? Then one would wonder if this universe has an open boundary or a closed boundary. Thus the answer will remain different from different persons as per their view of the universe. Scientists in general are interested in mathematical or physical concepts that can be realized in the real world using laws of finite. Since infinity as an entity is not accessible in their domain, the subject has hardly any relevance to them. It is important to point out some of the popular misuses of this term in scientific literature. For example, one would consider the following mathematical entities to be correct. Okay, so is this clear? Okay, that this concept of infinity is very ill understood even in the scientific community. So even in the scientific community, the concept of infinity is very ill understood. So what we are talking of here is absolute infinity, and what people generally think infinity is a limit. limit means it's a potential infinity. For example, if you take a number and make it bigger and bigger and bigger, and after some time it becomes out of your reach and you say it is infinite. But that is not real infinity, right? That is just a huge number. But the real infinity is a different concept altogether. And the first mathematician who was able to recognize this concept was, anybody knows the answer? The name of the scientist who first formulated the notion of, yes, George Cantor. So George Cantor was the first scientist to be able to formulate a mathematical idea of the real infinity, not the potential infinity. Potential means like this, these are potential infinities. If you say limit x going to 0, 1 upon x, so this you say it's infinity, but it is not infinity. It is still whatever value of x you take, it will be a finite number. And the concept of limits is like tending to a potential infinity, not the absolute infinity. Okay, in equation 1, infinity is not a natural number. By definition, so you know 1 upon infinity is not 0, 1 upon 0 is not infinity, 1 upon 0 is undefined, 1 upon infinity also is undefined. In equation 1, infinity is not a natural number. By definition, if n is a natural number, then n plus 1 is also a natural number, which is not true at infinity, right? You cannot say infinity plus 1 is infinity plus 1 means another number. No. Infinity does not follow the laws of finites. Hence, the division operation as given in 1 is not mathematically valid unless one assumes that the infinity is a very large natural number. So basically, they assume that infinity is a very large number, so it's a potential infinity, not the real infinity, and that's how they do the calculations. But that is not what is the real meaning of infinity. So that is why they often end up in problems also. So that is why the concept of real infinity was important, and that's why George Cantor's contribution is important. Okay. Equation 2 is often used in mathematics as well as in other scientific disciplines and is accepted as a valid operation. However, a careful examination of this operation will lead us to understand that the right-hand side is simply a very large natural number, but not the actual infinity, right? So it's a large number, you can call, it looks like infinity, like very huge number, but it is not the actual infinity. Here our argument is that operations involving infinity are not amenable to current mathematical operations. In other words, mathematical operations within finite domain cannot generate infinity. This is important. Mathematical operations within the finite domain cannot generate infinity. So you can say 1 plus 2 or 1, then 2, then 3, then 4, and you go on, and finally you will reach infinity. No, you will never reach infinity like that. Infinity is a different concept altogether, right? So, okay. Anybody has any questions here? Otherwise, we'll continue. In the pre-Cantor era, so George Cantor is the one who gave the definition of real infinity. So before him, mathematicians looked at infinity as potential, but not actual. It was accepted that infinity is simply a very big, large number. As you can see, Gauss, his reference is there. His paper states that. Interestingly, George Cantor figured out infinity as an actual mathematical object and not just a very large number. So, George Cantor formulated the mathematical understanding of infinity. Consider the set of natural numbers 1, 2, 3, 4, so on. This sequence is potentially infinite, as every natural number has a successor even after many enumerations, as the process of enumeration can only remain finite, right? It will never end. It will go on and on. And you may say, oh, it will reach infinity. But no, it will reach some big number, but it will never be infinity. It will never end, basically. The succession never ends. Consider a set of integers as I equal to all the integers. This set can also be written as, now they are counting infinity. They are saying, okay, how do you count infinity? How do you count a set which is which looks like infinite? So okay, so the cardinality of the entire the set of all natural numbers, that is infinite. So which means so what is the last number here? The last number is not defined, right? You can keep going. There is no last number. But the whole set, the cardinality or the size of this set is denoted with a mathematical concept which is called infinity. This is the mathematical understanding of infinity. Now the question can be asked, okay, you have got integers which are like +1, -1, +2, -2, everything, and then you have natural numbers. So which set is larger? The set of natural numbers or the set of all integers? Which is larger? Right, the question is, you have set of natural numbers, the total number of elements here is infinite, right? It never ends, and you have a set of integers where also it is infinite, but it is infinite in both the directions. Then if you go plus, positive side again never ends, negative sign, negative side, it never ends, right? So which one is larger? Which set is larger? Both are equal. Okay. Yes. So correct answer, both are equal. Both are equal. Now somebody can be confused. Why both are equal? Because this set is infinite on both sides. I mean, it is unending on both sides, the integers. A natural number has a limit in the because before 1 nothing comes, and on the other side it is unending. Then how are both of same size? Then so Cantor was the first to give this concept. He said you can count. How you count? You say, okay, I will group them in a different way. Instead of writing them in negative and positive sides, I will write them like this. I will write 0, and then +1 -1, then +2 -2, then +3 -3, in this way, right? And then I can say this set has a one-to-one correspondence with the set of natural numbers. So how do you count things? To count things, I establish a one-to-one correspondence, right? Let us say if I have to count number of balls in a bag, then what will I do? I will take this ball, I will assign it or make a correspondence with 1. Take another ball, make the correspondence with 2. Another ball, make a correspondence with 3. In this way I make correspondence with every ball, and when I am over, when all the balls are finished, that number I say, oh, this is the number of balls here, right? The process of counting is establishing one-to-one correspondence between the set of natural numbers and the objects which we are counting. And now the task is to count the number of integers. So I can do the same. So I will call 0 as 1, then 1 will become 2, or -1 will be assigned 3. In this way I can count, and this counting will never end, right? I can write a mathematical formula, like I can find exact correspondence for every integer to a natural number. That exact correspondence I can find. Like any integer you give me, I can find the corresponding natural number. So this means that both integers and natural numbers, they have same size. Means the sets have same size. So both are infinite. Okay. Once one looks at the set as a whole, then the set becomes actual infinity. So the size of the set is actual infinity. So this is Cantor's concept of infinity. Cantor argued thus that there exists a full-fledged mathematical object that is infinity using set theoretic approach, and demonstrated that this object does not follow the mathematical laws observable at the finite scales. His argument for the existence of such an object was supported by the well-proven existence of irrational numbers like √2 and 5. If one does not accept the existence of infinity as a real mathematical object, then these irrational numbers will cease to exist. So Cantor said that infinity is a real object. Means it is not an imaginary hypothetical concept. It actually is a true concept, because he says, you see, the irrational number like under root 2, it never ends. So what is the size? That is infinity, right? Because the moment you end, it is no longer under root 2, right? If you truncate the decimal at some point, then it is no longer under root 2. Under root 2 means it has to be unending. Okay, what is exactly meant by a mathematical object? It means a mathematical concept. A mathematical concept. Under root 2 is a mathematical concept. So mathematical object. So object, okay, you know the meaning of object in general. Object means anything which can be discerned from something else. So two objects are objects when they can be distinguished. So under root 2, and so under root 2 is one number, an irrational number, and there is another number called 1.414. There is another mathematical object. They are different, right? Because under root 2 is 1.414 and then so many other digits. And 1.414 is just 1.414. So you can approximate under root 2 with 1.414, but they are not equal. So they are different objects. They are different numbers. Okay. So the meaning of object is any two discernible concepts in the space. In this case, the space is the number line, right, which contains both rational and irrational numbers. If one does not accept the existence of infinity, then under root 2 and 5 won't exist, right? Okay. Now there is a set of natural numbers, there is a set of even numbers, there is a set of odd numbers. Which one is bigger? So you have the set of natural numbers, which is all the natural numbers. You take out half of them, means all the odd numbers you take out. What remains are only the even numbers. Then which set is bigger? The set of natural numbers or the set of even numbers? You can clearly say, right, the set of even numbers plus the set of odd numbers is equal to the set of natural numbers. So which one is bigger? Yeah. But it looks very counterintuitive, right? You take one set and take another set, add the two sets, and final set is there, and you are saying that all three have same size. This does not make sense, right? It looks very counterintuitive. When you add something to something, and this is not a small thing, both are of equal size, looks like, right? This much we can agree that odd numbers and even numbers, both these sets are of equal size, right? Everybody will agree to that. And you are adding the two, and what you get as the output is of the same size. It is not bigger. That looks very counterintuitive. Additions don't apply at infinity, yes. That is why this you can say now because George Cantor has given the concept. Before George Cantor, nobody would accept that. Even after George Cantor, mathematicians did not accept it. They gave so many arguments, they ridiculed George Cantor, but finally they accepted. But they had to be convinced very hard because they were not ready to accept that this concept is meaningful concept. Okay, and actually it is very true. I was discussing with one professor in Japan. I was discussing with him the concept that in spiritual world, happiness keeps on increasing. It never decreases. And he was so confused. He said, how is it possible that you something keeps increasing and never decreases? That will become larger and larger, and I don't think that is correct. So he didn't believe. Maybe he has not read that much mathematics, but it is true that similarly in spiritual world, the happiness keeps increasing and never diminishes. Okay. So this is the thing. Consider a set of natural numbers. If one takes out the set of even natural numbers, then what remains is a set of odd numbers. One can notice that that which is subtracted and that which is the net result are both same size, but also the original set is also of same size, and all are same cardinality, infinity. Okay. Now let me ask you a question. Can you have a set which has size bigger than the number of natural numbers or the set of natural numbers? Can you have a set which has a size bigger than the set of natural numbers? Real numbers. Okay. Did you read it in a course, or you are guessing it? No means what? You have read it, or are you guessing it? I have heard countable, uncountable, infinity. Okay, but these are both countable. Okay. Yeah. So real numbers consist of two parts. One are rational numbers, one are irrational numbers. So if I say just the rational numbers, is this set bigger than natural numbers or smaller than natural numbers? The set of rational numbers, just the rational numbers, is it bigger than natural numbers or smaller than natural numbers? Nobody's answering. Set of rational numbers. Okay. So I think the next section will explain that. Okay. This is just completion. Given one set of natural numbers, one comes across. So it's just establishing the one-to-one correspondence. You can read this. Okay. One can establish one-to-one correspondence between the set of natural numbers and the set of even numbers, as shown in figure number 2. Right? Just twice of that. Using these principles, readers will be able to see that at the level of infinity, the superset and the subsets are all of same size. Now consider the rational numbers, which is far dense compared to the natural numbers. It is known that between any two rational numbers, however close they may be, we can find another rational number. Right? You take any two rational numbers, in between them you can find infinite number of rational numbers. So still Cantor showed that the set rationals is of same size as that of the set of natural numbers and is countably infinite. The set of rational numbers is shown in the figure. Okay, this is a set. So you see, rational numbers means the numerator is a natural number and denominator is a natural number. So basically it is like this. So you have a natural number 1, put it here, another 1 put in the denominator, then okay. So all numerators are 1, all numerators are 2, all numerators are 3, all numerators are 4, all denominators are 1, all denominators 2, denominator 3, denominator 4. And you write it like this, and then you can go along the diagonals like this, like this, like this, and you can keep counting. You can assign this is 1, this is 2, this is 3, this is 4, 5, 6, 7, 8, 9, 10. There are some repetitions. You can skip the repetitions if you want. Like 1 upon 1 is same as 2 upon 2 is same as 3 upon 3. You can skip that, no problem. Right? So, but the thing is, you can still count all the rational numbers. You can establish a one-to-one correspondence between all the rational numbers and all the natural numbers. Readers can see that every sequence, both in rows and columns, is an infinite set. However, by indexing the rationals along the arrows as shown in this figure, starting from the origin and skipping the repeated entries, one will be able to generate the sequence of natural numbers, right? You can form the one-to-one correspondence. This implies that even a set of rational numbers is also countably infinite as that of the set of natural numbers. This discovery made Cantor to say, I see it, but I can't believe it. So Cantor said, this is unbelievable. Cantor made many other discoveries regarding infinity, but the interesting feature of his discovery is that at infinity, the whole is not greater than the part. The infinity does not follow the same laws as the finite numbers do. So laws of infinite are different from the laws of finite. Okay. And tomorrow we will discuss the Vedanta concept of infinity, which is very profound. Very profound. Okay. So with this, maybe I can add small thing. So infinity also can have levels, like set of natural numbers is the smallest set of infinity, and you can have bigger infinity, bigger, and you can have bigger infinities also. But okay, for our discussion, this much is enough. Okay, there is one set of infinity, and so infinity is an object. This is in itself a big achievement to be able to see how infinity is a real object, and it is different from finites, and even the laws are different, the operations are different there, and it all looks very inconceivable. Okay. Anybody has any questions? Otherwise we can stop. So, fine. Please give an example of infinity greater than natural numbers. Yeah. Irrational numbers is one example. Irrational numbers are greater than infinity. The reasoning why irrational numbers are greater than infinity, I think I explained it in the class once, means in our mathematics course, MSO 209, MSO 209 or 201, that class. How irrational numbers are cannot be counted, means they are bigger than, that this set is bigger than the set of natural numbers. That will be, maybe you can read or maybe we can discuss tomorrow. Tomorrow remind me before starting, I can tell how set of irrationals is bigger than the set of natural numbers. Right? Any other question? Okay then, Hare Krishna. Thank you very much.